But in reality, if that's the case, I'm going to show some actual data. This is showing the amount of polymer adsorbed. We are talking about PVA, a water-soluble polymer, onto silicon dioxide at a pH of 3.7, which is close to so-called PDCl IEP, which means the surface charge is almost zero, which means, okay, I do not have help from electrostatic charge. I'm just seeing the polymer effect. Yeah, and in this case, okay, and as we increase the polymer concentration, PVA gram per liter, right? Yeah, increase per liter, and we have as we increase the polymer concentration, we have higher and higher coverage on the polymer coverage on this ceramic powder surface. Here we are using milligram of PVA, per meter square of silicon dioxide surface. If you know your particle size, you will know how many of this one, right? You can convert from this one, if you know the particle size, convert from this one to a weight percentage of polymer versus powder, if you know the silicon dioxide particle size. Make sense? So, okay, naturally, the higher the polymer concentration, the higher the so-called relative surface coverage by polymer. And then let's look at the amount of polymer added on the particle surface. It also depends on whether the surface is clean or not. Here I'm talking about polymer attaching to the ceramic surface. I'm showing amount of polymer, amount of adsorbed what? PVA polymer onto ceramic, which is silicon dioxide, versus so-called calcination temperature. So I have silicon dioxide powder. I would heat treat this before I put that into the solution and add PVA. I put the powder, heat them up to what? Different temperature. I have silicon dioxide particles. I heat them up in air to different temperature. What do? Essentially, I'm trying to make the surface cleaner. It's a ceramic. It resists oxygen. So by heating up to different higher temperature, I remove the surface, the dirty stuff, which can burn away, the already attached groups that can evaporate away. And because of that, after I heat treat them to a higher and a higher temperature, I can have a even higher polymer adsorption because the surface now become even cleaner. I can have more of that my PVA molecule attached to the surface. Okay. And another one is about molecular weight. Here I'm plotting same. How much polymer adsorbed onto the silicon dioxide surface, but the horizontal axis is PVA, this polymer molecular weight. And what you find is for the same pH, I control for the same pH, the higher the molecular weight, the higher my surface absorbed total amount, relative amount, for both pH concentration. For both pH concentration. Okay? The higher the molecular weight, the higher the surface coverage. Not by too much, but a slight increase. Here it's exponential increase in molecular weight. Here it's roughly 50%, 30 to 50% increase in the polymer adsorbed amount or coverage ratio. Okay? So, okay. Other than the so-called polymer molecular weight, concentration, and the so-called solvent quality and temperature would also have an impact on the um, stabilization, so-called steric stabilization. Stabilization coming from polymer chain repel each other. And for a polymer dissolved in a solvent, and people would observe the stability of that suspension depends quite often on the solution temperature. Depending on the solution temperature. And what people find is above certain temperature, the suspension appears to be more stable, while below certain temperature, the suspension is less stable. Okay, so what kind of like people believe happens was above the certain temperature that we roughly here, the free energy change due to the polymer in the penetration is positive, which means the polymers do not really want to interpenetrate each other. And the solvent in this case is referred to as a so-called good solvent. The polymers would spread out more. The polymers would spread out more. On the other hand, the polymers would spread out more and they appear larger. On the other hand, if at lower temperature, the total free energy change due to the polymer in the penetration is negative, which means, okay, the polymers wants to kind of like coil down, shrink together, and solvent in this case would be kind of referred to as so-called pore solvent, and the polymer tends to recoil more tightly, something like this. Kind of like same polymer, still more random in its packing, but at higher temperature, the as you can imagine, the polymer molecules spread out more. Lower temperature, spread out less. Actually, this is probably also related to the kind of entropy. Higher temperature, higher randomness, spread out more. Lower temperature, coil together. Okay, and the transition between the kind of more spread out versus more recoil together, the temperature we can call it theta, or critical flocculation temperature. Critical flocculation temperature. What that means is if my suspension is below this temperature, my suspension would have a greater tendency to flocculate or particles come together, even though I have what? Polymers attached to that surface. Okay. So this one is about the absorption of polymer on particle surface and the solvent quality effect. I'm plotting amount of absorbed what? Absorbed PVB, polyvinyl butyryl, versus polymer concentration in the suspension. Okay, so I'm plotting how much of the polymer actually got absorbed onto the particle surface versus polymer concentration. But then I'm using two different types of so-called solvents. Okay, and my solid is what? What is my solid? Aluminum, 30% by volume, aluminum. But the polymer, this one is non-polar polymer, PVB. And the solvents that we are using are less polar solvent. Still slightly polar, but less polar. One is methanol. The other one is this MIBK methanol mixed solvent. Okay. So what we see is that, okay, our polymer, which is PVB, is nonpolar. Nonpolar polymer, And if we wanted to cover the solvents well, but to cover, sorry, not solvent, the aluminum, our particles well, or have higher absorption, if our solvent is highly polar, it's less polar than water, methanol. It's less polar than water. It has relatively what? Lower. For the same polymer concentration, it has relatively lower coverage. Compared with, we have this MIBK, methanol mixed solvent. Here versus here, I'm talking about two different types of solvent. One is pure methanol. The other one is methanol and MIBK mixed solvent. So essentially, for the top one, we are adding less polar or less polar solvent of MIBK, and actually majority of it would be MIBK. But I still have a little bit of methanol left. By making the solvent, the overall solvent less polar, I'm having what? More absorption of the PVB, not PVA, PVB onto the aluminum powder. Okay, so this kind of like this is related to the solvent quality, because for PVB, these types of non-polar polymer, the more polar solvent would be so-called a quote-unquote bad solvent. Within this PVB, within MEOH, it does not really want to stretch out. It does not want to interact with the solvent. On the other hand, the less polar solvent, BK, this one, is less polar, more closer to my PVB polymer. So they like each other. The polymer stretch out more, spread out more, instead of coil together, become a bead, or have kind of, you can imagine more of or less like phase separation here, but here it's more uniformly dissolved. Okay. Okay. So that's what we said. Okay, less polar MIBK added into the polar solvent. We are making better interaction between the solvent and the polymer, and as a result, we are promoting the polymer adsorption onto the ceramic particle surface.